Thanks a lot for the invitation. It's really a pleasure to be here. And let me tell you what this talk is about. It's going to be really about the use of semi-definite programming, and in particular, something called, generally speaking, semi-definite hierarchies for problems in quantum information. And here's an outline. I mean, this is going to be pretty introductory. Hopefully, if you have questions, you'll stop me and and we can clarify those. And I really want to emphasize somehow the basic ideas and results and the intuition. I mean, why these kind of things work, rather than perhaps incomprehensible or overly technical. And somehow the kind of things I want to focus is on, just very shortly at the beginning, at least a geometric viewpoint on semi-definite optimization, which I think is very useful. Then somehow I'm going to describe shortly at least one motivation to come into all these hierarchies, which is what happens as you move on from quadratic forms to polynomials. And we're going to see immediately how that allows us to answer questions, for instance, about consistency of moments, or questions about, for instance, entanglement and separability. And then we'll move on to kind of the non-commutative versions, because we're going to see that somehow it's exactly the same thing. I mean, you move on from commutative to non-commutative stuff, but this formulation of the semi-definite programs is essentially the same. So what's semi-definite programming? I guess we've used it already, but I want to again emphasize a couple of things. It's really like a generalization of linear programming to symmetric matrices. So instead of having linear inequalities in scalar variables, now what I'm going to have is inequalities in matrix variables, or positivity is going to mean that things have to be positive semi-definite. Right? And I like this geometric picture of semi-definite programming. I will not write things in coordinates as much as I can avoid them. And the idea is that what semi-definite programming really is about, we have the cone of positive semi-definite matrices. We're intersecting it with a certain affine subspace. Let me call it L. So my feasible set is intersection of this affine subspace and my cone. And I'm minimizing some linear function over this intersection. So it's really a cone, a subspace, and I optimize over this intersection. And just as a comparison, if this cone was a orthant, the non-negative orthant, this would be exactly linear programming. But in here, we're changing the cone with something which is not polyhedral, and somehow many of the same features you'll see will apply, although a few things are going to be slightly different. There's tons of applications. I mean, the last 20 years or something, there's really an explosion of applications in semi-definite programming in many, many different areas. Particularly in combinatorial optimization, control theory, I mean, of course, quantum information, and say a little bit about this. And why this is nice, again, I'm going to abstract out how do we actually solve it. But the reason why this is nice and convenient is because it's a nice class of convex finite dimensional optimization problems, but a little bit more than that. I mean, it's not the kind of things, for instance, that we could just apply the ellipsoid algorithm, a general purpose convex optimization method, but there's a lot of structure in here. This is defined by determinants, we have nice computable Barber functions. So there's a lot of things that we can do in here that parallel very much what we can do in the linear programming case. For instance, there's a beautiful duality theory that pretty much has exactly the same features as in linear programming. And this is going to come in very useful. We're going to see even in the kind of things I'm going to describe today that somehow it's very, very convenient to not just look at your primal formulation of your optimization problem, but you also want to look at the same time what happens in the dual, and you can carry a lot of information from one place to the other. And these things are essentially solved all in polynomial. So
What's the essentially caveat?
Well, the essentially caveat has to do, depending exactly on your, so in here, for instance, as opposed to linear programming, in linear programming, if data is rational, solutions are rational. Yeah. In here, that's not necessarily the case. Mm-hmm. Yeah. So then, so what you're talking about in here really has to do with computing epsilon approximate solutions. Right. Yeah. Right. And encoding issues. Okay. Solutions can be exponentially big, actually.
I see.
So semi-definite programming in quantum information, as I said, it has, there's been a lot of applications in the last 10, 15 years. These are some names. If your name is not there, and it should be, let's rewind and write it. And more than anything, the only things that I'm going to focus on is a little bit on some work that we did like 10 years ago on entanglement and separability, and somehow kind of the corresponding, I'm going to use this as a segue into perhaps one of the things that I think many of you are kind of interested in, which is how do we characterize a set of quantum correlations of moments, and how that allows me to compute perhaps values of games, or approximate values of games, I should say. So in the title, we have all these semi-definite hierarchies. I'll describe specifically what I mean, but let me perhaps take a step back and try to discuss at a high level what these things are actually trying to do. And to me, the two key features that these things are trying to do is, on the one hand, is of course you're really trying to approximate some difficult object that you don't know how to handle. And this could be a set that perhaps it's non-convex, or even if it's convex, it could be like it could be very computationally difficult to describe, and we're going to see some examples of that. And somehow the way that these techniques work, or again, there's many ways of interpreting them, but one in particular I think it's useful is that essentially what they try to do is, instead of looking at this object globally, what they try to do is they try to satisfy local consistency conditions. And I write local in here in quotes because I don't really mean local. Depending exactly on whether we're talking about LPs or we're talking about semi-definite programming, then we're talking about some kind of reduced, if you want, consistency conditions. And somehow, of course, there's this all parable, whatever, of the blind people, trying to fill an elephant, and that's exactly what happens in here. I mean, each constraints that you impose, there will be a description, but there's nothing that will actually guarantee that all these things can actually fit together into a nice global object. I mean, if you like topology, it's kind of homology issues, essentially. Right? And again, we're going to see exactly how these kind of things appear. This is not a formal definition, but somehow I really want to emphasize that there's kind of these two things. I mean, on the one hand, how do we deal with approximation of sets? And the way that we actually do this is by somehow imposing some kind of low-dimensional consistency conditions of a certain type. So this is something that, I mean, at least in spirit, appears all over the place. In particular, in optimization, we've been doing this for 50 years or something in different versions. Of course, now we have a much more sophisticated way, hopefully, of thinking about the things. But for instance, when this idea of approximating convex sets using linear programming, linear programs of a particular type, I mean, people have used things called linearization reformulation, roof duality, Sherali-Adams relaxations all the time, and those produce somehow polyhedral approximations of convex sets that they have nice properties. And there's a lot of philosophically related ideas in a number of areas. I mean, if you like probability, the idea of locally consistent marginals. You have a joint probability distribution between many variables, and perhaps along every subset, things are consistent, but there may not be a global object. Right? And there's a number of other areas where the same kind of thing is true. So one thing at this level even, yeah, sorry.
I should think of the hierarchy as going less and less local, or?
Less and less local, exactly. It will become clear later. Yeah, but essentially we're imposing stronger and stronger conditions that hopefully will bring you closer to the existence of a global object. Right. So if you like LP, for instance, and you want to understand a little bit what's the difference between the kind of things that we did before with LP and the kind of things that you can do with semi-definite programming. Think about LP as imposing, again, in particular situations, as imposing consistency conditions between subsets. Right? So we may impose, if we have a joint probability distribution, for instance, that whenever I restrict this candidate joint probability distribution to all subsets, somehow what I see is actually consistent. Semi-definite programming will do something different. They will say that on every subspace, things will have to be consistent. And of course, you could pick subsets that are subspaces that are aligned with coordinates, some subspaces of the form 1, 1, 1, and all zeros. But there's a lot of other subspaces. And somehow semi-definite programming is going to be very strong, or much stronger than LP in that sense, because it's going to impose stronger consistency conditions rather than just about subsets.
You mean linear subspaces?
Sorry?
You mean linear subspaces?
Yeah, linear subspaces.
So why linear subspaces you couldn't formulate with linear?
Because you have infinitely many subspaces. Right? When you look at subspaces of fixed cardinality k, you'll have n choose k. If you look at all possible subspaces, you'll have an infinite number. Somehow that doesn't fit into finite dimensional LP. It's really infinite number of constraints, and that's exactly semi-definite programming. So what's nice about this is that we have very compact ways of describing these things, as we're going to see. Somehow, in a sense, at least, I mean, of course, that's in the eye of the beholder. I think the semi-definite picture is much easier than somehow the LP picture, because everything becomes linear algebra instead of combinatorics. So somehow, of course, depending on your taste, if you like combinatorics, then you love these kind of things. But somehow linear algebra, at least, it's a lot easier for at least certain things. You have a lot more symmetries. Actually, that makes things very, very nice. Okay, so let me start perhaps with I mean, there's no technical content in here, but anyway, if there's any question or... Okay, so let me start with something perhaps more concrete. And let me try to address a very old question or very natural question in applied mathematics, which is, let's imagine that I have a polynomial, a multivariate polynomial, right? And I want to try to understand whether this polynomial is non-negative, right? So I have a polynomial in n variables in here of degree d, whatever d will have to be even. And I'm trying to understand whether this polynomial is non-negative whenever I plug in all possible variables, right? And in here I'm working over the reals. Everything that I'm going to say will extend to other domains, but just to make things simpler and not have to make things difficult, I'll just deal with global non-negativity of a polynomial. So of course, if p is quadratic, that's easy. I have a quadratic form, I check eigenvalues, or actually, I just check if a matrix is positive semi-definite, I'm done. But if the degree is greater or equal than 4, then that's already NP-hard. I give you a quartic polynomial, we cannot efficiently decide whether this polynomial is non-negative or not. It's NP-hard as a function of the number of variables. Right? There's an obvious...
I guess cubic is trivial because if you have a cubic term.
Odd degree, so if you have any odd degree polynomial, as you go to plus or minus infinity in some direction. There's an obvious sufficient condition. If I have my polynomial and I can write it as a sum of squares of some other polynomials q sub I, then obviously this implies this. Right? And what I like about this, I mean, what many people like about this, of course, is that you don't have to trust me that I got this, that I'm telling you that my polynomial is non-negative. I actually have a certificate, these q sub i's in there. If I just verify that these two things are exactly the same, that's actually certifying that my polynomial is non-negative. It's not as if I were to run, let's say, a quantifier elimination algorithm, Tarski-Seidenberg or something like this, that will run in your computer for 3 weeks and end up telling me yes or no. And we don't know whether kind of my computer, my program was fine or had a bug or anything like this. It actually happens. Many of the quantifier elimination software is very buggy. So, so what's nice about this, again, somehow very easily verifiable certificates of non-negativity. And much more interesting for us is that this is a semi-definite problem. The existence, deciding the existence of such a decomposition, whether I give you a polynomial and checking whether my polynomial is a sum of squares or not, is a semi-definite problem. I'll tell you very briefly how it works. It's not crucial for what we're going to do. I mean, it's crucial that it's a semi-definite problem. The details are not crucial. And this is really the building block. I mean, everything that we do afterwards, they're just kind of either dualizing or putting slight variations on this. So if there's one thing I want you to remember is that whenever you're faced with non-negativity, that's a horrible problem. You're faced with some sort of condition that's great. And we're going to see why, for instance, if you care about entanglement, you actually care about these polynomials even though you may think that you don't.
And this sufficient condition, is it like in typical cases always true?
We'll talk later about that. For now, the only thing that I'm saying is that this is a sufficient condition that implies this. Let me perhaps make a couple of comments, two cases where you do know that these things are equivalent. One is, of course, if P is a quadratic form. Right? If P is a quadratic form, it's quadratic, then the eigenvalue decomposition, the factorization, Cholesky decomposition, whatever you want, will tell you that this is true. Because if you have a quadratic form, you factor, it's a sum of squares. The other case, it's a little bit less trivial, but equally trivial, is a univariate case. If I have a polynomial in one variable, you write the roots, you play around with you factor the polynomial, you play around with the roots, and you'll be able to easily write a decomposition of this type. And there's a few other cases. Hilbert actually exactly characterizes the cases where these things happen. Yeah.
Following up on Scott's question, in the univariate case, we also understand the odd. You can talk about odd degree if you just look at positive axes. Yeah. Something similar you can do just on a cone.
Same thing. I mean, there's versions of this if I want non-negativity not on Rn, but I want, let's say, over a compact region or a cone or something like this. All this machinery applies. Slightly different versions, but essentially the same thing.
Is it also true for matrix-valued polynomials?
Yes, it's essentially true for matrix-valued polynomials. Actually, the univariate case, it's essentially a result by choice. Yeah. Actually, many people reprove that, but in particular. Yeah.
Here you're saying that semi-definite programs are useful to test non-negativity because they can test for some...
I don't directly check this, I check this.
Right. So is there a sense in which this problem is sort of universal for semi-definite programs? I mean, is it...
Well, it's reducible. I mean, you can go either way, right?
So any SDP is
Essentially, you're really checking. I mean, when you have an SDP, you really have an affine family of polynomials, and you're trying quadratic polynomials, and you're trying to find one on that family that is a sum of squares. Perhaps you cannot reduce it to the case of is this single polynomial a sum of squares or not, but what you do is you form a pencil or an affine family of polynomials, and you ask, is there one which is a sum of squares in this family? And that's actually going to be important somehow. We're going to move in just a second from the fixed polynomial case, I give you P and you tell me yes or no, to I'll give you an affine family of polynomials and you'll tell me if there's one that's a sum of squares. So again, let me just describe in one slide. I don't think the details are terribly important, but at least I want to give you a plausibility argument why it's actually a proof, but why this checking this condition is a semi-definite problem. So the idea is very easy, right? So the idea is that if I have a polynomial of even degree b, it's not very difficult to see that my polynomial is going to be a sum of squares, if and only if I can find a positive semi-definite matrix Q in such a way that I can express my polynomial as a quadratic form in a vector Z, where Z is essentially a basis for the space of polynomials of degree up to d over 3. Right? And in particular, I can just pick this polynomial basis, right? This monomial basis. And why somehow this is an if and only if? Because if I have my polynomial and it's a sum of squares, I can just write my sum of squares as linear functions on this vector of monomials. Then when I put those two things together, I get a matrix Q. And conversely, if I found a matrix Q that has this property, I factor it, and I will get a decomposition. Now, the only thing that we need to show is that this condition, they're essentially linear conditions in Q. Right? And that's easy to see, right? Or it's a semi-definite problem. What do we have in here? Q has to be positive semi-definite. Q lives in my cone. What is this, really? Imagine expanding this expression. What I have in here is a polynomial. What I have in here is another polynomial. If I want these two things to be the same, I will just match coefficients. What are the coefficients on this side? They're just linear expressions of the coefficients of Q. So somehow the identity between these two things, they're just linear equations between the Q sub ij's in here and the coefficients of P. That defines a subspace. If I want to find whether this is true or not, I have to find a positive semi-definite matrix on that subspace. So this is exactly a semi-definite problem. If you're concerned about the size of the semi-definite problem, how big is Q? Maybe use a board. So that's essentially of size. I have all the monomials of size up to over 2. So that's n plus d choose 2 plus 1 d choose 2. Remember, d is even. And this is actually, let's say for fixed d, this is polynomial in d. Polynomial in n. Sorry, actually polynomial in both. Whenever you fix any, it's polynomial in n. So it's clear. Again, the main point, if you hand me a polynomial and you ask me is it a sum of squares or not, I'll write this semi-definite. I won't write it. I'll tell my computer to write this semi-definite program to solve it. It will tell me yes or no. And if it is, it will give me a certificate. It will be a matrix Q that I can verify that it's not. If it's not true, it will give me a certificate that this polynomial is not a sum of squares. And we'll talk later about what these kind of things called. Good. Questions? Okay. So why do we care about this? Why do we care in optimization about these kind of things? Because it's a one step to go from a fixed problem, from a fixed polynomial to optimize it. Right? The only thing I need to do is to really think about, okay, let's say that I'm trying to minimize P. I have a polynomial P, like this one, ugly, non-convex, whatever, and I'm trying to minimize it. Now let me write it in a different way. Instead of trying to go down in my polynomial, let me try to go up from the other side and try to find out whether I can find a lower bound gamma on my polynomial. And finding the minimum is exactly finding the largest gamma in such a way that the polynomial P of x minus gamma is non-negative. Right? So I have a polynomial, I'm trying to find the minimum. I can just take constant, push it up as much as I can, and as long as this polynomial is non-negative for all x, that means that P of x is greater or equal than gamma for all x. Right? And of course, now we can go from this non-negativity conditions that I told you they're ugly and difficult to a condition of this type, where I try to find the largest gamma that satisfies that P of x minus gamma is a sum of squares. And this we can do just with a semi-definite program exactly the same way that I was doing it before for a fixed P. Why? Because I play the same game, writing the condition that this has this quadratic representation and matching coefficients is going to give me linear equations between the entries of Q and the coefficients of this polynomial. The coefficients of this polynomial are linear functions of gamma. So I'll have on the one hand linear functions of Q, on the other side linear functions of gamma. These are linear equations, and that's fine. I can just maximize gamma subject to those equations. Right? So this is, again, really important that just in the same way that we deal with a single polynomial P, I can just deal with affine families. I can think about, I have an affine subspace of polynomials. I'm trying to find one in that family, which is a sum of squares. Right? Yep.
Can you somehow incorporate the gamma into the variable?
Yeah, gamma is a decision variable. Yeah, exactly. So now the decision variables of my semi-definite program, they're simultaneously going to be gamma and the Q sub i's. And I solve for both at the same time. Or let me perhaps take abstracted away. If before I told you that semi-definite programming was this idea of I have a cone of matrix and a subspace, now let me just abstract all this stuff out and just say that now the problems that I can solve, there I have the cones of sum of squares and I have subspaces of polynomials. And then I don't care anymore about semi-definite programming. Semi-definite programming is under the hood. But the only thing that I care about is I have, as long as I have affine families of polynomials and I have a cone of sum of squares, I can find points in these intersections. And underneath, I will write them as semi-definite programs. I don't need to ever write a semi-definite program if I want to deal with this.
Is this a special case of SDP, or are all
It is.
SDPs
I mean, because in the
writable
particular case where you take polynomials with quadratic, these are quadratic forms, these are matrices.
So it's not known how to reduce a general SDP to this form?
Well, if I allow more parameters, it is.
Ah, okay, okay,
Yeah.
okay.
It is exactly.
Okay.
Good. So this is on the polynomial side. Let me just mention very briefly what happens on the dual. I told you that every time that you have a complex problem, there's a corresponding dual. And I just want to mention it briefly. There's a nice interpretation somehow in terms of moment consistency. So somehow the question that you want to add, again, forget out what I said before for a second. So the question that I want to answer, for instance, in here is imagine that I actually give you a candidate set of moments. And just to make it easy in these examples, let's imagine that I'm doing in the univariate case. And I'm interested in a measure, for instance, in the existence of a measure or a probability distribution, which is consistent with a given set of moments. Right? So for instance, in this case, I may be interested in knowing if there's a probability distribution that has 0 moment 1, first moment equal to 0, mean equal to 0, second moment equal to 2. And of course, the answer in that case is, of course, there is one. Right? What's an example? So this is just a normalization condition. This is 0 mean. And I want variance equal to 2, so just pick, Gaussian, whatever. You pick the Gaussian of 2 times the standard, or square root of 2 times the standard Gaussian, and I know that will tell you that there's a density which is consistent with those ones. Right, but what happens in this example? Right? I mean, can you find a probability distribution whose first moment is 1, that's just normalization? I want the mean equal to 2, and I want the second moment, the expected of x squared, equal to 3. Sorry?
Probably violates modern equality or something.
Essentially Cauchy-Schwarz, yeah. But yeah, sure. I could cite my most general inequality also. Yeah, I believe. Yeah. So this will. I mean, it's easy way of saying this. For instance, if you remember, the variance is always non-negative. The variance is the expected value of x squared minus the expected value of x squared. If you compute in here, you'll have that the variance of this random variable, if it exists, it should be equal to -1. So clearly, these numbers are not consistent with an underlying probability distribution. Right. So let me try to, and of course, you're seeing where I'm heading, right? I mean, you're interested, many of you are interested not in probability distributions, or you should be, I guess, or you are, but you're particularly interested in the quantum case. And somehow, if we understand this case, then essentially the same techniques are going to generalize. Right? So why this polynomial stuff that I was telling you before gives an answer to this? Because, of course, there's an equivalent characterization, I'll tell you what that star means in a second, of when a set of moments is actually, they're actually consistent with an underlying probability distribution. Essentially, the only thing that you need is that the expected value of all functions, they have to be non-negative. All non-negative functions, they have to be non-negative. And I'm working here on a compact set, so that's why I know because polynomials are dense, I can just look at non-negative polynomials. Right? So the point is, and let me perhaps make this a little bit more explicit. Instead of my somewhat ad hoc argument about variance, let me try to explain that argument in a different way. Let me say, for instance, that I'm smart, and I'm trying to compute the expected value under this whatever probability is, if it exists, of something like x minus 2 squared. Right? And let's compute what this is going to be. By expanding this, I don't even know how to expand the square. So this is minus 4x plus 4. Then I can use linearity of expectations in here, right? Because I know that the expected value of x squared is going to be equal to 3. The expected value of x is going to be equal to 2. So this is minus 8 plus 4, and this is minus 1. Right? So what happens in here, I'm computing the value of some polynomial that should be non-negative, and if there's truly a distribution, this should give me a positive number. But in this case, I get something negative. Right? So the point is, if I were to test in here against all possible non-negative polynomials, and I pass, this would be great. I know that at least on compact sets, there has to be a corresponding probability distribution. This is what's called the truncated one. Sorry? So I would, in here, put all polynomials of this form, and I would require that this is positive for all polynomials. And in here, I'm failing. Right. So somehow what happens in here, what's a way that we're producing semi-definite approximations of this, that instead of checking against all polynomials of all degrees, we're just going to check on all non-negative polynomials, we're somehow only going to impose the consistency conditions that I have to produce non-negative values whenever I compute expectations with respect to polynomials which are sum of sums. I mean, somehow this will give me some kind of outer approximation of this set that I want. Right? Again, think of that as an example. Well, let's get to quantum finally. So why should you care about polynomials if all this stuff was a little bit weird? Let me tell you that this I reckon, just by essentially turning the crank, this immediately tells us a very nice way of approximating the set of separable states. Right, so I think here I'm looking at bipartite quantum states. We know, or you know better than me, that I'm looking at essentially convex combinations of product states. I'm looking here at the density matrix, right? And of course, a question which is pretty hard is if I give you state in here, I give you a rho, I want to try to understand whether it belongs to this convex set or not. And notice that convexity doesn't actually help me in here. Remember what I said at the beginning, that even if I start with a convex set, if my convex set is difficult, then I know that by itself doesn't really help me a lot. And of course, one may be interested not just in membership to this set, but if you're interested in solving some other problems, you may want to optimize over this set and understand, for instance, what happens when you optimize over this set. So what I want to see is that it's fairly natural, or essentially translating what I said before to this domain, we can easily produce nice approximations for this set. And this is all work that we did like 10 years ago or something, with Andrew and Federico. Okay, so what's the idea? Somehow what is a key? Is that if I have a convex set and I have a point which is not on the set, then the obvious way of certifying that that point is not, Kanbana, right, separating hyperplane, will tell you find the separating hyperplane that puts your state on one side and puts your separable states, your set, on the other side. And this picture is nice and wonderful, right? I mean, it's very easy. I have a convex set, I have a point, I find it. What's the difficult part in here? The difficult part is, given this subspace, to actually check that this set is on that side. This part is easy, right? I mean, if I have a subspace, verifying that on one side is easy. The difficult part in here is to verify that this set is completely contained in the half space defined by this. Right? And it's kind of well known, again, many of you know a lot better than me, that there's a perfect identification between these kind of separating hyperplanes that leave the separable states on one side with something called positive maps, essentially maps that will map positive semidefinite matrices into positive semidefinite matrices. And I'll tell you why that's essentially equivalent to looking at non-negative polynomials of a certain type. what's called bi-Hermitian polynomials. These are going to be polynomials in two sets of variables that are quadratic in one set and quadratic in the other set. Right? And again, this has a number of names in the quantum information literature, but this is a well understood, or operator theory, and this is kind of pretty well understood. So why somehow were polynomials appearing here? If you're if you're not exposed to this viewpoint, it may not be obvious in here that you have somehow some nice underlying polynomial in here, but it's actually pretty easy. Right? Because the idea is, if you want to check whether a hyperplane is non-negative on a convex set, it's of course enough to just check on the extreme points of your convex set. Right? And I can easily parameterize the extreme points in here, because the extreme points in here are exactly tensor products of rank 1 matrices. Right? And if I write it down, let me just write it this way. If I write this linear function applied to a separable state, what I'll get when I expand it is exactly a polynomial that looks like this, which is biquadratic. When I fix the x's, it's quadratic in y. When I fix the y's, it's quadratic in x. And when I mean quadratic, I mean Hermitian. In here, we're doing the complex version. Right? So it really looks like this. For if you give me w, let's say w is your favorite witness in here, I mean just a whole bunch of numbers, then the condition that this actually is on this side, that the set is on this side of my hyperplane, really boils down to the question of whether this polynomial is non-negative or not, for all values of x and y. So I'm sweeping over all possible extreme points of this, and I have to get a non-negative number. Of course, at this point, I'm setting you up. We cannot do this. This is non-negativity. What we're going to do, we're just going to write the sum of squares condition on this. And again, don't worry about complex versus real. I mean, we have sum of Hermitian squares, same stuff. Right? So what happens if we do that? Is this clear? Questions? Good. So what happens if we do this? This is great. It does give you an approximation of the set. And of course, this is something that people did know about in somewhat different form. Like, in those terms, this class of positive, remember I told you there's an isomorphism between these different things. So somehow the polynomials that have sum of squares witness, they correspond to something called the composable maps in operator theory. They correspond, or the sets that those things can detect is something called PPT state, possible partial trace states in quantum information. So it's great. I mean, we do get an approximation of this set, but we cannot refine this, or yet. Right? The way I present it, we just get another approximation that may be bad or may be good. We don't know. But now is exactly where the hierarchy parts enter. Where not only I'm going to be able to produce this, but I'm going to be able to produce more and more and more approximations in here, and I'll tell you in a second how we do this. Right? Is this clear? Why we get... Remember, somehow instead of identifying all the possible non-negative polynomials, I'm just identifying a smaller subset, which are the ones that are sums of squares. So in this picture, that gives me a coarser approximation of my set, so the approximation is going to be bigger. Here, it's just duality. Right? I make things smaller on one side, they get bigger on the other. How do we make this? Dory, you have a question?
Yeah, I'm not sure. What is the PPT states?
PPT are the ones that when you apply a partial transpose, you get a positive semidefinite matrix. And there's states, like the ones in here, like the ones in here, that will have a...
so these are the entangles, so they seem...
Yeah, exactly.
Okay.
Yeah, they would seem entangled, but yeah. Okay, so what happens in the... How do we make this stronger? So let me just explain it first because it's easier in the polynomial case. I mean, let me ignore the quantum stuff for a second. But the idea, again, it's a one slide, actually one equation, which is this. That if I want to put conditions that are somewhere in the middle between P being sum of squares and P being non-negative, and again, for simplicity, let me just work on the sphere. Let me make, P homogeneous. Let me deal with a homogeneous polynomial. Right, then something that I can do is just do something like this. I can take my polynomial, and I can multiply it by something positive. Let's say, in particular, the sum of the squares of my variables raised to some power k. It doesn't matter. K will matter. So it's, again, immediate, that this condition is weaker than this. If P is a sum of squares, when I multiply it by another sum of squares, the product is also going to be a sum of squares. But this still implies non-negativity. So as I increase in there, the multiplier, the power k that I'm using, I'm getting better and better conditions that approach this non-negativity. And it's not very difficult to show in full generality, people have done this, extremely complicated settings, but let's say on the sphere or in the homogeneous case, elementary arguments will tell you that as k goes to infinity, then essentially we're approaching this cone. So if you want in this picture that I had before, if you have one set and another set, you're getting layers and layers between one and the other, and essentially as k goes to infinity, this fills a cone. Right? Yeah.
So are you saying that any non-negative polynomial can be approximated in the limit by a product of sum of squares polynomial?
Ratio of sum of squares.
I'm sorry, by?
A ratio of sum of squares, right? Well, I have that this, I have that this is a sum of squares, so that means that P is a sum of squares divided by this. And that's essentially what Artin proved right now when he solved Hilbert's 17th problem. Okay, so we take that, we translate it in here. If before we just looked at witnesses for which this expression was a sum of squares, what am I going to do? I'm going to take this, I'm going to multiply it by something, and I'm just going to check whether this is a sum of squares or not. I'm going to be looking for witnesses of this type. If you do that, you'll get nicer classes in here that get closer and closer to the set of separable states. And again, as k goes to infinity, these things converge. So here's an example. If you want, this is from the paper. I don't remember which state we're looking. We're looking at one of these difficult states. So you look at a particular witness, you multiply it by this XX transpose, and what you'll see is that this actually has a nice decomposition even with integers of this type. Right? I mean, this is again just an example. Yeah.
So here you made the choice of multiplying by this
This?
Yeah. So
yeah.
Are there cases where there would be a better choice or a different?
Yeah, and certainly, for instance, if this is fixed, I can search for a multiplier. That's also a semi-definite problem.
So SDP will search for the multiplier.
If I fix this, if I fix my witness, then I can actually search for the best multiplier in here.
When in general you're trying to find a witness such that...
Yeah, so in general what you do is you just use this. I mean, certainly the things that we defined would just fix, kind of that multiplier to that. Yeah, I mean, in the stuff that we did, we just fix it to this. Okay, so let me mention very briefly the dual, an interpretation that also I think many of you are familiar with, which is somehow like before I told you there's a dual story, there's also a dual story in here. If you don't like entanglement witnesses and you'd rather think just directly in terms of the state.
Just a quick question.
Yeah.
Is that, is the particular choice of the xi squared to the k, you could optimize it, but can it vary by a lot in terms of the degree, or is there?
That's something that we don't, even in the general case, we don't understand very well. Even in the polynomial case, there are certainly cases where if you pick that very, very carefully, you can get away with certificates of low degree. If you use something universal like this, then you may have to somehow make things longer. Yeah, I mean, higher levels.
And that's a huge difference.
And we don't know examples where there's a huge difference.
Well, look, I mean, the fact that deciding separability is NP hard, right, or, optimizing over separable states is NP hard, sort of tells us that there must be some cases where K has to increase.
Oh, of course, yeah. No, but right. Yeah, but that's a different question, right?
Okay, all right, fine.
Sorry, what's the most general thing to put there instead of...
In here? Oh, an arbitrary positive polynomial. If you know any positive thing to put in there, but then you have to have a certificate that that's actually positive, if you actually want to prove something. Yeah.
Does this have anything to do with the hierarchy of k extendable states?
Of course, yeah. That is
It's the same thing.
that hierarchy. I mean, that's what we defined in that paper. That's what this slide is about.
Okay. Sorry, and can you dualize the duals? Can you identify dual matrices? Like for PPT, these were decomposable maps, and
well, you get the class of I mean, it's hard to characterize it other than in terms of this. but right now they're essentially the things that have certificates of this type, that you only need to multiply it once by something until they become sums of Hermitian squares. Yeah, it's somehow tautological. We don't have an intrinsic definition of what do they mean.
I mean, before it was positive decomposable. It would be nice to see what are the
Right. Yeah.
objects.
Wait, Pablo, is this an accurate characterization? You want to witness, there's normally like a measurement on systems AB that's, but it should be one that if you write M on AB plus M on AB prime, then that resulting operator should be positive semi-definite?
Yeah, so that's kind of like essentially what will happen here, right?
But I mean,
when you do the extension.
but if you say on the first level, what are the witnesses? Well, those are the decomposable witnesses. But then if you say, what are the witnesses that correspond to a higher level of the hierarchy? Would they be the ones that you know, satisfy that property I just said? Or no?
I'm not sure.
Okay.
I think, yeah. I have to think about it. Yeah.
Are there entangled states that you reach for no k, or is it really
So
converging?
what we really, no, so we don't get, you don't get in general, you get that the closure of this will give you the whole cone.
Sorry?
You get that the closure of this, or you take the union of this for all case,
Yeah.
and you take the closure of this, and that will give you the set, sorry, the intersection, right? You'll get the set of several sets.
So essentially, if I would run my algorithm forever with increasing case, I would at some point.
Yeah,
get
it will always
the
succeed.
answer.
Yeah, for anything.
Yeah.
Yeah, it's a complete hierarchy. I mean, that's exactly right. So what's a dual viewpoint? Again, like I told you before, you have consistency of marginals in the classical case. What happens in the quantum case is a story about symmetric state extensions, right? So instead of thinking of my original bipartite state, I may think, okay, if my state is actually separable, then I can actually write down explicitly some kind of extension of my state to more parties, right? Or somehow the property that this state will have is that it's going to be symmetric between these two parties, let's say 2 in here, or k in general, and also when I do a partial trace over all these other components, I get back the original state. And it turns out that you can decide that separable states will always have these extensions, entangled states cannot have these extensions to an infinite number of parties, or sorry, to a sufficiently large number of parties, and this is if you check the existence of the conditions, sometimes the only thing that it's involved in there are either linear equations or semi-definite conditions. So this is a semi-definite problem, and in fact it's exactly the dual of the stuff that I described in the previous slide. So somehow this makes very clear the picture that I was telling before, that it's really about consistency of a certain type. Right in here, it's consistency.
Case match?
Sorry? Yeah, it's exactly the same case. Yeah, so if I want in here extensions to k parties, then that gives it.
Choice of multiplier you made makes this.
Yeah, exactly. This is where you see the sum of the x sub I squared, essentially. Because I exactly copied this in the other components. Yeah, if I were to pick something different in there, then I'm doing something different in here, and I cannot quite understand. I mean, I do know what it is in the probabilistic case. I don't quite know exactly what will happen in here. Essentially, it would correspond to normalizing the cone in a different way. I mean, what you're really doing is you're making this compact by taking a section, the sum of the x of I is equal to 1, and then you're taking a different compact section of the same cone, which I think will be like a different normalization condition. But again, I don't know the exact answer. Very quickly, the 3 slides that I have, 2 minutes I have. So one is, of course, this should ring a bell, and it's exactly somehow the equivalent of the classical De Finetti theorems in probability. The Finetti theorems in probability will tell you that if you have a sequence of random variables that's infinitely exchangeable, then that's equivalent to being a mixture of IIDs. And somehow what's underlying all this story is some finite versions of that that were worked out by Diaconis and Freeman, and somehow the quantum versions of this, both finite and infinite, that were worked out by a number of people. And in particular, something very nice that comes out of all this work is that you can actually, something that we certainly didn't do, which is, it gives you a nice way of quantifying how well these things do as a function of k. So if you want to know how well you're approximating these sets, and you're giving a certain error, and you want to understand what k you need, and think of k again either as the degree of this, the exponent of this multiplier, or the number of copies, then these kind of theorems will actually tell you how you should pick k if you want to guarantee that this will happen. And there's a number of different results. I decided not to put any because they really vary in terms of how you pick norms, if you're measuring things in one norm, 2 norm, LOCC norm, and of course Fernando, and I guess a number of other people are kind of who you should ask for these kind of things. So in the 1 minute that I have, let me just tell you, kind of how this generalizes, for instance, for the non-commutative case. And the idea is it's exactly the same. You don't need to even think about this. At least if you want to write the corresponding conditions, if you want to analyze them, of course you have to work. But if you just want to understand what happens, it's exactly the same thing. What do you have now? If you have a non-commutative polynomial, you can have a non-commutative polynomial in operators or matrices if you want. There's a natural notion of positivity. I want this to be positive. There's a notion of sum of squares. I want to have a quadratic representation of a certain type. The semi-definite problem that you write is exactly the same. You write this, you write monomials, you expand, you match coefficients. And essentially what you want to understand is how to approximate this kind of nested convex bodies that we saw last time, right? I mean, there's a polytope of classical correlations, there's a quantum convex set, and there's a no signaling polytope. This is easy, this is combinatorially hard, it's essentially a cut polytope, and this is a thing that we don't understand very well, which is exactly the kind of things that you want to optimize over when you want to compute values of gains. And what you would do in this case, for instance, if you want to compute the value of, let's say, some game of this type, and this is in the paper by Andrew, Liang, Ben Toner, and Stephanie Vedder. So what you're really trying to do is to maximize a function that looks like this over A's and B's. A and B's, and there are the POVMs of the two players. So instead of requiring that this polynomial be non-negative, I mean, a spectral value, an eigenvalue condition on this is essentially a polynomial being bounded below by gamma. You just try to find a certificate that that thing is a sum of squares. And if you also increase the degree of the multipliers, you get exactly the kind of semi-definite hierarchies that they obtain, or dually the ones that Navasquez, Asin, and Pironio, they obtain in this case. So it's exactly the same picture. What's the tricky part? These arguments, which I have to say I don't really understand very well, on the question of finite dimensionality, right? Whether you can achieve these things in the optimal values in finite dimensions, and I don't think these things are yet tell us anything about that. I mean, perhaps there's a way of extracting something from prime and dual solutions, but I really should wrap up. Shameless ad, we have this nice book with a number of people on the near with all the stuff at the beginning. You don't have to buy it, you can search it on the web and you'll find it. But the idea is that, again, somehow there's a very nice way of just approaching this. Siam will not be happy if I say this, but that's fine. Actually, no, they allowed us to do this, so I'm not doing anything wrong, either morally or legally. And the idea is that, again, somehow if we just focus on this sum of squares type conditions, I mean, many of these things, they really come very naturally. I mean, it's either positivity conditions on commutative variables or non-commutative variables, and the techniques are exactly the same. I mean, nothing really different. Good. Thank you. Any questions for Pablo? Yep. Yes, it does. So there's a very nice result by, I'm forgetting, Plenio, oh, I didn't write it. What's it? Plenio,
Navasquez,
yeah,
Owari, and
yeah, Plenio, Navasquez, Owari, they show that the convergence rate that you get is actually better when you include the PPT conditions than if you just look at the symmetric extension condition. Essentially, it goes from something like L, so like 1 over L to 1 over L squared. Navasquez, Navasquez, Plenio, and Owari.
Excuse me, what's L?
L, my K, sorry, K. They go from 1 over K, if you don't impose a positive condition, to 1 over K squared.
I just have a comment. You see the equivalent between exchangeable and symmetric in the commutative case, due to all this, which is somewhat different, is false in the non-commutative case.
The equivalent, sorry, say that again?
Between symmetry and exchangeability. I mean, exchangeability and subsymmetry is false. So this theorem fails. It's true in the commutative setting, but fails in the non-commutative setting. So there are variables which are sort of getting more and more independent over their tail, but they're not exchangeable anymore.
Right, yeah. In here, essentially, what you use or what provides a completeness are these results by Helton and McCullum. So they prove the non-commutative version of the positive Schelling sets that kind of applies in this sense.
Yeah, but that's, yeah, okay.
Right.
Just to make sure I understood the last part of what you said, for the field theoretic value of a non-local game, you can approximate it sort of from above, like converge on it, but you can't just approximate it because you can't get lower bounds. Is that correct? Or
The question, what's not clear in here is, so the way that this formulation works is working from below, right? So it's, and what it's not clear is whether you're actually converging to the true value, whether there's a finite dimensional strategy that will produce that value. You're producing lower bounds,
okay.
But it's, I mean, we don't know, apparently, again, I'm not an expert on this, that we can achieve these ones in finite dimension. Right, exactly, yeah. Yep.
Way back in your first slide or something, you made a comment that I kind of been asking how seriously you know that you were making an analogy, I think, to the relaxations used in the crypto, the Grosvenor basis relaxation.
Yeah.
And it's finite fields and everything, so how?
So essentially what you do, I mean, it's very similar to what you're doing in here. Instead of looking at quadratic equations, you linearize. At polynomial equations, you linearize, you introduce new variables for finite products, and then you just treat them as linear equations in this. Now you're doing exactly the same thing. The difference is that you also impose the positivity conditions that are coming from this. And the problem is, of course, we cannot do this over finite fields. At least, I don't know. Yeah. But, I mean, conceptually, it's exactly the same. Kind of you just linearize. The point is in here over reals. We know more valid constraints that are true. And those are coming from that.
And maybe if I could steal a second question. So you, in fact, refer to the order problem. So does anything here work? So if I start with a rational function that I want to show, so does any of this framework?
So this is much more general than what I described. Essentially, an arbitrary semi-algebraic problem, you can write this kind of relaxations. As long as it's semi-algebraic, you can do kind of these kind of things.
Okay, if there are no further questions, let's thank Pablo again.